Okay, so we'll be solving problem number 15. Okay, this problem involves a cantilever beam of length L embedded at one end, and we are tasked to find the deflection of the beam given that it is subjected to a uniform force P. So the cantilever beam seems to be this here, and it has a fixed end, and then it is subjected to a uniform force P. Okay, now we are tasked to find the deflection of this beam with respect to a certain point chosen to be x and y. Okay, so this kind of problem involves a fourth order differential equations, involves the Young's modulus of elasticity and the moment of inertia. Now from the equation we have already established, we can say equation in the form of a differential equation. We have the Young's modulus of elasticity times the moment of inertia and times the fourth derivative of y with respect to x with respect to x is just equal to the force it was subjected to. Now, since that this is just an ordinary differential equation at higher degree, then we can use a undetermined coefficient method to solve for the solution for this differential equation, or just by simply integrating this 4 times successively, we can now get the solution, which is the y. Now, if we integrate this one, we'll just have to divide both sides by e over I, and then we get for the next equation p over e and then I. Now, if we integrate this 4 times, what we get is the solution of this differential equation in the form y of x is equal to c1 plus c2x plus c3 x squared plus c4 x cubed plus our particular solution, which is p over 24 e times I x to the fourth. Now, our task here is to find the constants of integration c1, c2, c3, c4, and c4, so as to find the real equation of deformation between the two cantilever beams. Now, finding this one, we need the boundary value problems, in which it is subjected to constraints at the free end and at the fixed end of a certain beam. Now, since we have a cantilever beam fixed at one end and we have a free end here, the constraints could be y of 0 is equal to 0, y prime of 0 is equal to 0. Then for the free end, we have y double prime of L equals 0 and y triple prime of L equal to 0. Simultaneously solving these equations and then using equations in two unknowns, we can now get the values of c1, c2, c3, and c4. Now, to begin, we have okay. From the general formula, we have y equal y of x is equal to c1 plus c2x plus c3 x squared plus c4 x cubed plus p over Young's modulus times the moment of inertia x to the fourth. Getting the first derivative with respect to x just be equal to c2 plus 2c3x plus 3c4x squared plus and this is 24, okay, was 1/6 times p over e I x cubed. Now, since we have the primary equation that y prime 0 be equal to 0, then we equate this one to 0 and the c2, then this equation, this quantity here all becomes 0 plus 0. Thus we have c2 being equal to 0. At first, we have also the boundary equation, the boundary value y of x, y of 0 equals 0. Thus, we can only directly substitute 0 here and then x, 0 for x. Automatically, we can get 0 equals c1 plus all this becomes 0, 0. Thus, we have again c1 equals 0. We have now the values of the two constants, c1 and c2. Next target is the c3 and the c4. Now, looking back into the constraints we have written, we need the third derivative of the solution so that we can, the second and the third derivative, so that we can get the value of the c3 and the c4. From the original, we have y double prime of x is equal to 2c3 plus 6c4 x plus 1/2 p over ei x squared. And we have the boundary equation, a boundary value problem, y prime double prime of L is equal to 0. By equating this one to 0, we have 0 is equal to, and replacing L for x, we get 2c3 plus 6c4 L plus 1/2 p over e I, is I, L squared. We have now equation into unknown c3 and c4. We'll mark this as equation number 1. And again, we have the third constraint goes like this: y triple prime of L is equal to 0. Right? Now, solving for the third derivative of this one, we get y triple prime of x is equal to 6c4 plus p over e I, moment of inertia, times x. And we are subject to the constraint that it is y triple prime of L also equal to 0. From the previous ways we've done, we equate this 0 and then replace x for L, L for x, we get c4 plus PL equal to E times I. Okay, now we can directly solve for the C4. So just erase this one, and then C4 now directly we can solve to be equal to negative P times L over 6 Young's modulus, so this is times the moment arm. We now have the value for the C4. So what's lacking is that the C3, in which we can use equation 1 because we have already the value of C4, and then solve for C3, we will now have the value of the unknown C3. Now using this formula, we get 0 equals 2C3 plus 6. Substitute this one, it will be to get negative PL squared over 6 E times the I plus 1/2 this is just equal to 2 PL squared over 2 E times I. Okay, now rearranging, we get C3 equals, then we'll just transpose this one, this 2, this will become positive, negative, and then divide both sides by 2. We'll get 2PL squared minus PL squared all over 4 E times I. Okay, then if we further simplify this one, we'll get C3 now becomes P L squared all over 4 E I. Now we have now the values of the 4 unknowns in our solution for the given differential equation in fourth order. Now summing up all the results and then plugging in the values of the 4 constants into the solution of the differential equation we've obtained, we will now get the equation of the deflection of the cantilever beam subjected to force P, which originally we have the solution y of x equals C1 plus C2x plus C3 x squared plus C4 x cubed plus P over 24 E times the I x to the fourth. We have the values for C1, C2 to be equal to 0, C3, and the C4. Now substituting the values, we get y of x equals, this always comes to 0, and then the C3 equals P L squared over 4 EI times x squared minus the value of C4 is negative, so we get PL over 6 EI x cubed, and of course the value of this function. And we clear the area. This one will be plus P over 24 I x to the 4. Now this is the equation of the deformation produced by force P on the cantilever beam with length L.